Hi, my name is Marco Russo and I want to talk about the VertiPaq Analyzer. In the next 20 minutes, I will show you how VertiPaq Analyzer is a tool that can help you to optimize your Power BI desktop model or your analysis services database, locating and maybe removing those columns that are not so useful. So before starting, let me show you what are the tools that you need to follow up this session. Here we have two links. We will see DAX Studio and VertiPaq Analyzer, which are two tools that you can freely download and install on your machine. Actually, VertiPaq Analyzer is embedded in DAX Studio, and you need the second link, the VertiPaq Analyzer one, to import the data of VertiPaq Analyzer in an Excel file for more detailed information. So let's try to see what we can do with a demo. We will spend most of the time in a demo. And I start with a simple database, which is a Contoso database that is 250 megabytes large in a file on disk. This is because this file has a large sales table that we can see here in the diagram view that is connected to many other tables, and this table sales has 12 million rows. Now, I know that the table sales is large. You can see the size of the table sales in this corner here of Power BI Desktop. But we can have more detailed information about the cost of each column. Because of the compression algorithm of the engine of Power BI, each column is compressed in a different way. So in order to analyze this information, we have this tool embedded in DAX Studio, which is called VertiPaq Analyzer. First of all, you have to install DAX Studio, and then you can launch DAX Studio with this button as an external tool. If you have a version of Power BI Desktop like July 2020 or a following version, the integration with DAX Studio is automatic, and you see the button in the external tools ribbon of Power BI. Once you are in DAX Studio, you have in the Advanced tab these three buttons here, Import Metrics, Export Metrics, and View Metrics, and we want to click this one, View Metrics. View Metrics retrieves statistical information from the model that you have, in this case the Power BI Desktop Contoso model, and fill this pane that has a number of tabs that show a number of information. And I want to start with a summary, because the summary basically shows me the total cost of the entire model, which is 300 megabytes. This size is always larger than the file size of the PBIX file, because the PBIX file has a further compression. So the data in memory is compressed, but not at the same level that you have on a zipped file like the PBIX file. So this is the information about the cost of storing this data in memory, and in tables I can see the cost of each table. So let me enlarge these columns. The numbers that you see here are in bytes, and I want to just give you some quick information about what we have in each of the columns here. So let's start with the name of the tables. As you see, now I'm sorting the table names by the column size, but I of course can choose other columns, but this is usually a good enough choice in order to make the more expensive table to be the first in the list. And as you see, sales is the more expensive table. The total cost of all the columns and of the entire table, sales, is 312 megabytes. And the cardinality here, the first column that you see here, is a column that tells you how many rows you have in the entire table. Now, cardinality is a column that has a different meaning depending on the object that we analyze. When we analyze the tables, the cardinality corresponds to the number of rows of the table. However, if I drill down here and I explore what is inside the sales table, you see that I have a list of columns. Each column of the table sales corresponds to a row in this list. And the column names have been sorted by the column size. Moreover, you see that the column size also has like a small bar chart that tells me the cost also in a graphical way. And you can see that the cost of a single column in the sales table here is 97 megabytes. So this column is large, is almost 30% of the entire table. And the cardinality here is identical to the cardinality of the table. Now, the cardinality, when you look at a single column, the cardinality is just the number of unique the number of unique values that you have in that column. And when this number corresponds to the number of rows of the entire table, the column corresponds to a primary key of the table, a column that has a unique value for each row of the table. Guess what? This kind of column is very expensive. But this column is necessary if you have one-to-many relationships between the table and other tables. For example, let's take a look at another table. The customer table has 18,000 customers. And if I drill down, you see that the customer key column has exactly the same number of rows of the entire table. So the cardinality of the customer key column corresponds to the number of rows, which is not the same for name, because we might have 2 or more customers that have actually the same name. So name is not guaranteed to be unique, whereas customer key has to be unique because it is used also in relationships. So you need a unique column when you have a one-to-many relationship with other tables, but for the sales table, this is not a requirement for the data model. Yes, of course, you probably have such a column in the data model, but maybe that I don't need to import this column if I don't need to create one-to-many relationships between sales and other tables. So I already have a very quick information. I just analyzed 2 columns, and I already know that I can remove one column in order to save 30% of the table. But I have a more accurate information. If I go on the right here, you can see that there are columns specifying the cost of the column here. Let me zoom this a little bit. The cost of the column we have here is 30% of the entire database and 31.21% of this table. So we already have a ratio between the cost of the column and the cost of the entire table and the entire database that helps you understanding the impact of what happens if I remove the column. Of course, sometimes you cannot remove the column, but just being aware of the cost can help you making better decisions. So let me just do a quick example. So what happens if I remove the online sales key from this model? I can go back to Contoso, I can go to my sales table here, and I right-click and remove. Let me just make sure I choose the right column here, online sales key, good. And I delete this column. Of course, I have a confirmation now, and when I remove the column, I don't actually need to refresh the entire table. But if I go back to DAX Studio, you see that the column is still here. Why? Because I didn't refresh in DAX Studio the information about the statistics. We don't do this automatically in DAX Studio because it could be expensive, so I click on View Metrics again. At this point, the information is refreshed here, so I go back to the sort by column size, I open sales, and you see that the column disappeared, and the size of the table has been reduced of almost 100 megabytes. This is also visible in the summary, where you see that the size of the entire data model now is 210 megabytes. And if I save the PBX file, I will see that I shrink also the file size. Now, of course, VertiPaq Analyzer has many more information, but the first and more useful one is understanding the impact of each column in the model. But we have time, so we can investigate a little bit more about other details of this model. So let me show you what is the meaning of the other columns. You clearly understand that the table is an information here. This column table makes sense only when I have information about a table, whereas the side of the column is the cost of all the objects that are related to the column. So let me try to explain this when I go back here, so it could be simpler. You see that we have different information here. We have the hierarchy size, the dictionary, the data, the column size, and the table size. So let me try to describe this in a way that simplify the concept. So the table size is the size of all the objects related to the columns and related to specific information that are associated to the table and not to each specific column. For example, the cost of the relationships is not related to a specific column, is always associated to the entire table. And you see that the table size is slightly larger than the total of the column size, but usually the difference between table size and column size is minimal. The column size is the sum of all the structures that are specific to each column, so it makes sense to see the column size for a single column. So the column size for this column here, the first column we have here is order number, so the cost for order number is 82 megabytes. We found another column that is very expensive. And guess what? At this time, also the cardinality, the number of unique values of the column order number, is relatively high. We have more than 1.5 million unique values in the order number column. Guess what? We have, for each order number, we have several lines. On average, maybe 6, 7, 8 lines, and this, the multiplication of this average by the number of order numbers provides me the total number of rows in the sales table, 12 million. But 1.5 million is still a large number of unique values. And let's see what happens when we have a large, a column that has a large number of unique values. We see, yes, the column size is large, but why? We have three information here. So 3 pieces of information here. So we have data, we have dictionary, we have hierarchy size. So data is what is actually the cost for storing the data of the column in a compressed way. But when a column like this one has many rows with the same value, what happens? Usually there is a dictionary which is mandatory if the column is a string and is present or not if the column has a number. When the dictionary exists, when the dictionary has a number that is not just 120 bytes but 1 kilobyte or more, it means that there is a structure that has the list of the unique values that exist in that column. This way, the way to store the data is just by providing an integer number that is an offset to this dictionary internally to in the structure of the engine. Now, this way, even though we have a long string, the data required to store that value in the column is a small number, and this number can be further compressed with several techniques. For this reason, the data size usually is not related to the average length of the strings in a column. This column order number is a string. But these strings have been stored in the dictionary. So we have the string for each unique order in the dictionary. You see that the dictionary is bigger than the data, because the dictionary has strings that could be long, whereas the data only has an offset to the dictionary that is an integer number that can be compressed in a better way. If you do the math, you see that the dictionary size in this case is on average 50 bytes. And you will see this ratio for many other columns, also numeric ones. You have columns with numbers that have a dictionary, and the dictionary is still a list of the unique values, and the overhead to store each value in the dictionary could be large, especially if you have short strings. If you have long strings, the dictionary could be larger than 50 bytes per unique value. And so you realize that sometimes the cost of the dictionary is bigger than the data, and you have to realize, do I need this column or not? Yes, if you want to provide a way for the end user to filter a single order number, yes, you have to store this. But in case you don't need this information, you don't need this detail in your Power BI report, you could remove this information and you would save a lot of space. Or you could replace this information with a shorter number. This would just save part of the cost of the dictionary, even though remember that there is always an overhead, even though you have a very short string or just a number. But what is this hierarchy size? This is another information that is usually created to improve the performance of locating data in the column, and it's also necessary to enable MDX to work. MDX is another query language used by, for example, Excel when you query a Power BI model. So this hierarchy size can be disabled, is a structure that can be disabled in large analysis services databases, even though we don't have availability of this setting in Power BI yet, in Power BI Desktop. So At the moment, we have to keep this data in the model, in a Power BI desktop file, but knowing that this could be large is another element that can help you evaluating the total cost, the overall cost of a column. As you see, we have additional information like the encoding type. There are different encoding techniques to compress data in memory, and we have the data type and other details that are not so interesting at the moment. Because I want to provide you the more important information, and here you can just see that the difference between the table size and the column size is this column relationship size and user hierarchy size. There are two additional structures that are usually relatively small and don't affect the cost of the model in memory too much. So we have also number of segments and number of partitions. This could be very important in very large data models, and usually is not something that you can affect directly unless you reduce, for example, the number of the partitions if you see that you have too many partitions and too many segments in a model. However, the size of the segment is 1 million rows by default in Power BI, and you cannot change this, whereas is 8 million rows by default in analysis services, and you have a way to change this setting for analysis services, but in Power BI it is not available yet. Now, the information we have seen here are also available in the columns tab, and the columns tab just has a different way of presenting data. The columns are the same, but you see that here we have a table column that allows me to mix columns of different tables, because, for example, if I want to order by column size all the columns of the model, you see that all the columns come from the same table. But when you have many tables in the model, you want to quickly locate the more expensive columns for the entire model, and this is an easy way to retrieve the data. We also have this relationship tab, and relationships is interesting not just for the size, which is available here in this first column, but for the cardinality of the relationship. For each table, we have a list of the relationships that we have connected to this table. So, for example, sales has relationships with product, customer, promotion, store, date, and currency. Each of these relationships has a cost in memory, but as I said, the cost in memory, the size in memory is not really important. What is more important is this cardinality information. From and to cardinality is the number of unique values that you have on the two endpoints of the relationship. From is on the many side, to on the one side. So this information tells me that we have in the sales table 3 unique values used in the sales table, but the store table has a list of 306 stores. We have 306 unique values for the store. So knowing how many keys have been used in each relationship could be important, and also knowing how many missing keys exist on the many side that don't exist on one side could be important too. And this violation is something related to the referential integrity violation. Now, when you have in the sales table, imagine you have in the sales table a store key that doesn't exist in the store table, this will be an referential integrity violation. It's not an error, it's just a warning that appears that is more important for the data quality. It could have a small impact in the performance, but actually the more important thing is that you have to be aware that you have in your model data in the, for example, sales table that don't exist on the one side of some relationship. And this is a very easy way to retrieve this information here. And finally, partitions. As I said, in Power BI, you have only one partition in Power BI Desktop, but if you publish the model in Power BI Premium or in Analysis Services, you might have more partitions. And here, in case you have more partitions, you have the list of partitions for each table, which is another useful information. So once you have this data, you can export also the information I created now in a VertiPaq file. For example, I can store this data in this file. Let's call this Contoso VertiPaq file. You see that the extension is called VertiPaq. It stands for VertiPaq Analyzer, and this information allows me to import this data into another model, or into another instance of DAX Studio. For example, I can click on import matrix and I can open the same file, and I can send this small file to another user by email, for example, and it will show the same data. In the Excel file, you can also have additional information like the list of the measures and the list of all the DAX expressions you used in your data model. I suggest you to visit the link that you see here, the VertiPaq Analyzer tool, which contains this Excel file and instruction about how to use it. So I hope that you enjoyed this presentation and try DAX Studio, try VertiPaq Analyzer, optimize your model. Thank you.